Greetings, in this one let's talk about LU decomposition of this matrix. This matrix of 2, 5, 2, 1, 5, 4, a 2 by 2 matrix, and we want to do a LU decomposition example. And this is not the generalized case or derivation of this idea or proof. This is an example merely. So we have 2 by 2 matrix, and then we have L and U 2 matrices, also 2 by 2 ones, by whose product we want to describe A. So A should equal L times U. And what should L and U be? That's what we're going to talk about here. So that's LU decomposition. You can describe the matrix A as a product of L and U. And how do the two L and U are supposed to look? Well, L is supposed to look in the way that it has ones on the main diagonal, and it depends of course on the size of the matrix. But now we're dealing with a concrete example. We have 2 by 2 matrix, so we're multiplying 2 by 2 by 2 by 2 square matrices, of course. So we have 2 ones on the main diagonal, or 2 entries on the main diagonal, whatever the values are. L should look in the way that on the main diagonal there are ones, top right of that, all the entries to the top right of the main diagonal are 0, and the ones on the bottom are something. And U should be a little bit inverse of that. We should have a 0 on the bottom left of the matrix, and on the main diagonal are whatever numbers. So let's denote them like a line like this, and also whatever numbers on the top right rest of the matrix. So the main diagonal can be whatever numbers for U, and a 0 on the bottom left. And then there is some number on the bottom left of L, ones on the main diagonal and 0 on the top right. That's how U and L and U should look. And how is U yielded? Well, U is yielded in the way that we take Gaussian elimination of A in order to get basically the echelon form, where we have the leading entries going towards right, more zeros from the left side as we progress going down by rows. So we should, in the case of 2 by 2 matrix, get a 0 here. Once we get that, these entries can be whatever, this should be whatever, only a 0 should be here. Then we get U. And after that, we'll take care of what L should be. So all that we are now doing is just take care of what L and U should be. Alright, so that will be this following. U should be something, as I said, just repeating the same thing. U should be something that on the main diagonal you have whatever numbers, top right of it, whatever numbers, and 0 on the bottom left half of the matrix below the diagonal. And the way we get there is Gaussian elimination. So I can just say arrow and transform A by one matrix operation. Namely, I would subtract -5/2 of row 1 from row 2, because we will divide 2 by 2, then we get -1. We divide 2 by -2, we get -1, and 5 times that's -5, which cancels out this 5. So I'm just writing it below it. So we get a 0 here. Of course, row 1 doesn't change because we are subtracting it from row 2, and -5/2 away subtracted from 4 is same like 8/2 minus 5/2, that's 3/2. So that should be our U. This case is simple, it's a 2 by 2 matrix, so only one operation works. And by the way, one important thing to mention, it works not always. LU decomposition works when you can change the A matrix, the matrix A, into U in a way that you don't have to switch rows. You can do the other row operations like adding a row to another or multiple of a row to another row, but don't switch the order of rows. So as long as you can do it without the switching of the row order, the order of the rows, swapping the rows, you get U, and that will be fine. And now we got U. So now this should be basically U. Okay, U, all it should be is it has numbers on the main diagonal, numbers above that, and zeros on the bottom left. And of course, in this case, it's a 2 by 2 matrix, so there's just one space for 0 on the bottom left. So 2, 1, 2, 1, 0, 3/2. And what should L be? L should basically be yielded in a sort of interesting way. I'm not going to go into details. I would definitely recommend in this context to know elementary matrices and how they connect to elementary row operations. But basically, if you want to denote, and I'm only talking now about 2 by 2 case because that's what I'm illustrating here directly, take a 2 by 2 identity matrix. And if you want to represent a row transformation when you add, for example, the first row once to the second row, and you want that elementary operation to be represented by a matrix by which from the left you multiply a matrix that you want to transform in that following way, like adding its first row to the second, then you do that same operation onto the identity matrix. In that case, you would get this. So this matrix transforms the 2 by 2 matrix in a way that it adds the first row to the second. You just did the same thing to the identity matrix, and now this matrix, when you multiply by it, functions as that row operation. And in a similar way, we get L. We will look at what we did to U in order to get to the Gaussian form, post-Gaussian elimination. So from Gaussian elimination, what did we have to do? What elementary row operations? Of course, switching rows was impossible. But we will again take an identity matrix, 1, 1, 0, 0 in the 2 by 2 case. As I said, this is a very concrete case. And we will do the similar thing, but switched. So if we add it, we will subtract the row. If we subtracted the row, we will add it. That means that because we added minus 5 half times, we will now add it 5 half times, not minus, to the identity. So in the A, in order to get to U, only was one step. So this case is a nice example, simple 2 by 2 matrix, fast process in it. And just like similarly, and that's why it's recommended to know elementary matrices before going to this, and also knowing like how they represent the row operation. But once we get that, now we have a 2 by 2 identity matrix. Let's just take whatever operations we'll put onto A in order to get it into U. And that was just one operation in this case, minus 5 halves of row 1 added to row 2. And let's switch the polarity of this number. And that operation we will make to identity matrix, and that will become the proper L that will work. So because we added minus 5 half times, we will actually do 5 half times onto this matrix. We have 1 and 5 over 2, all right? And this is how it works. We can check it now. I will put the numbers into L. 1, 0, 5 half, 1. And let's check it. We can just check it by multiplication. Once again, there was a scheme for how L and U should work. Look, L should have ones on the main diagonal, U should have whatever numbers on the main diagonal. And then besides these things, L should have numbers to the left and zeros on the top right, and U should be in the other order. So numbers on the top right and zeros on the bottom left. Now by the process that I showed, we got a concrete L and U in this case. And let's check that it works. So doing the matrix multiplication, for example, in your head, let's check it for every entry. So we would get 2, that's fine for entry 1. We would get 2, we will get for entry 2 we get actually this is 1. 1 plus 0, so 1, fine. For this entry it's 5 plus 0, fine, and the last entry is 5 halves plus 3 halves, 8 halves. That's 4, so it's fine, it works. You see, we were showed by LU decomposition, or by LU decomposition, we were able to decompose the matrix A into the product of these two matrices, L and U. L should look in the way that it has ones on the main diagonal, and U should look the way that it has some numbers that not necessarily one on the main diagonal right here. And U was yielded by Gaussian elimination applied to U without switching, without swapping rows, and getting it into the echelon form.